Before a physical drone takes flight, we must ensure its algorithms work. Testing in a digital space prevents hardware from becoming expensive debris. To do that, the industry relies on a specific toolkit: Gazebo for physics simulation, the robot operating system for communication, and Python to write the logic. By the end of this setup, you will have a configured workspace, a running 3D world, and a custom Python script passing data directly into the simulation. You will need a computer with a multi-core processor, at least 8 GB of RAM, a dedicated GPU, and both ROS and Gazebo pre-installed. Checking these requirements now and configuring this digital sandbox ensures your code is safe and stable long before it touches a real motor. Step 1 is building your ROS workspace. This is the central directory where all your custom packages and robot code will live. Looking at this folder tree, we start by creating a catkin ws directory with a circ folder inside it using the makedir p command. Then cd into that new workspace. Next, run catkin make to compile the workspace, generating the build and devil folders. At this point, many beginners hit a wall. They write their code, but the system refuses to run it because the terminal doesn't know where to look. To fix that, you must run source delv setup.bash immediately. This command links your new workspace to the operating system. Without it, everything you build inside these folders remains completely invisible to ROS. With the workspace active, we need to start the physics engine. Instead of opening Gazebo directly, we launch it through ROS so the two systems can talk to each other. Type ROS launch gazebo ROS empty world.launch into your terminal and press enter. You should see a new window open, displaying this vast empty 3D grid. This blank slate is exactly what we want. It acts as a controlled environment where you will eventually place your custom robot models. Seeing this grid confirms that the communication bridge between your operating system and the Gazebo physics engine is fully active. With the environment running, it is time to write a ROS node, an independent process that executes specific tasks on the network. Open your text editor, navigate to your src package, and create a new Python file. First, the shebang, #usr bin and python, tells the computer to execute the file using Python. Next, rostie.publisher opens a communication channel named chatter to send string messages. Finally, a while not rospy.isShutdown loop transmits the payload exactly 10 times a second. Together, these lines transform a standard text file into an active broadcaster, pushing data directly into the ROS network. Before running the script, there is one last hurdle. If you try to execute it right now, the system will likely throw a permission denied error. You have to tell the operating system that this file is allowed to run as a program. Type chmod plus x followed by your script's name to grant it executable permissions. Now type rosrun followed by your package name and script name to start the node. Your screen should look like this. The 3D grid remains stable on one side, while your terminal continuously streams the data strings you wrote. This synchronized data flow is your proof. Your custom logic is now actively communicating alongside the simulated world. You have successfully linked your operating system, the Gazebo physics engine, and custom Python code into a single functional loop. Next, we will look at RViz, a visualization tool that takes the invisible sensor data your node is processing and renders it in real time. If you want to explore the specific parameters of your new environment, the official ROS and Gazebo wikis offer detailed technical documentation. Setting up this foundation is the exact first step you need before deploying complex navigation algorithms to a rover in a dynamic physical landscape.